prior problems in transient space, we've used this lump capacitance assumption, and the lump capacitance says the temperature inside a body is uniform at any given time. So it's obviously an approximation. There's no possible way that can be true, but it's good enough for certain types of problems. Now we're going to talk about situations where you actually want to capture both the time change of temperature and also a spatial change of temperature. So we're going to start out by doing that in one dimension. So this will be like a 1D transient conduction type problem. But before we get into actually the techniques for that, we'll do analytical and then numerical again. I want to just spend a slide or two, maybe three, talking through the concepts that are going to be important, right? So to start, let's look at this plot on the lower left. And let's imagine that we have, let's see, let me draw it here. So we have some fixed surface temperature. So imagine that you just have like a plain wall. You've got a wall, you're holding the surface at a temperature. And initially, that wall is at whatever room temperature. And, well, think about it this way. So initially, the wall is entirely at some ambient temperature, which I'll draw here. Let's call that T. So T initial. So T initial is down here. The entire wall is at T initial. And then at time T equals 0, I suddenly force this temperature of the wall to go to Ts. Right? So I started saying that backwards. But everything's initially here. Suddenly I force it to go to Ts. What happens? Right? So at time equals 0, what is that going to look like? Or time, let's say, shortly after 0. What is that going to look like? You're going to have some kind of really steep gradient here. And then it's going to go out like this. Right? So like just after 0, there's a huge amount of heat transfer. Like if you look at the dt dx, there's a huge amount of heat transfer going in because I'm forcing this temperature to occur instantaneously. So just after that, there's a huge gradient, and then most of the wall yet hasn't had time to see this disturbance. Right? There's a time lag associated with getting that heat into the wall. Right? Like intuitively, you can think about that. Right? It takes a while to heat up a pan or something like that. So that's at say time t, so t approximately 0. Now as we move forward in time, what's going to happen? You're going to start seeing this thermal wave move over. Right? The heat is going to start penetrating into the wall, and you get this gradient that develops. So it might look something like this, right? So time, this would be time 1. Let me draw it this way. Time equals 1. And we could draw time equals 2. And time equals 3, and so on. So at time equals infinity, if this is an infinite wall, right, this entire thing is going to come up to some temperature that's constant. If it's a finite wall and there's some other condition on the other side that's forcing, say, the temperature to be maintained here, at time equals infinity, you would get a linear profile. Right? Your plane wall temperature profile would develop at time equals infinity. But in the meantime, there's this sort of moving thermal front that's convex. Right? There's a convex temperature profile there. So let's use this concept to develop like a really approximate way of saying, well, how long does it take for heat to move? Like, how long would it take if I was sitting right here for me to actually see this thermal wave appear? How long would that take? And then some other time constants that'll go with this. All right, so the simple model we can do is let's do an energy balance. I don't know, let's pick time equals 2, for example. And I'm going to do a control volume at the time equals 2 wave front. Right, so this is at time equals 2, my thermal depth is right here. This is the furthest that the heat has actually affected. So I'll draw a control volume there. And then let's do an energy balance. So I have what I have in equals out plus stored. There's nothing here that's going out. Right? All the heat's coming into this face. There is heat going this way, but it's not leaving. Right? I've drawn the control volume specifically to coincide with the end of that. So the only things that are happening here, I have in and I have stored. Okay, what's coming in? Well, at x equals 0 right here, that's going to be conduction right at the, I guess you could say there's a convection matched right over here. But inside the domain, there's conduction. So that would be q dot conduction. Q dot conduction is, let's say, approximately equal to Ts minus T initial times K A over this delta T. So what is delta T? Because delta T, I'll draw it here, that's the thermal depth. Right? So at this time equals 2 line, we've gone delta T into the domain. Okay, so that is a resistance formula, right? We're going Ts to T initial, K area over delta T. Makes sense to everybody? So that's conduction. What else do we have? We have stored. So our stored energy, which we would call, I guess, du dt, right? What is our expression for U? So U is going to be, we could approximate it as saying it's the total mass of this control volume, M, times the specific heat, times the change in temperature, right? MC delta T, should look familiar. So the rate of change of that with time, we could write as follows. So first we'll say U is approximately equal to Ts minus T initial. So times what we need to get mass. So we need, let's see. Let's say we know rho in this situation. We know density rho. So we would need to have the volume that's involved here times the density, right? Volume times density. So that would be, the volume is going to be delta T times A. And then what? Then we have rho times C. One slight or minor point here is, okay, I'm saying that by writing it that way, I'm saying the internal energy change is all the mass inside this control volume is going from T initial to Ts. Because I've said the total volume is involved, delta T times A times rho times C. That's not quite true, right? We've got what sort of looks like approximately linear, it's a linear-ish temperature profile. So on average, the temperature is increased by, let's say, Ts minus T initial divided by 2. So this is my approximate model for internal energy change. So, okay, we bring this back together, and we would say, on the left hand, we have Ts minus T initial times K times A over delta T. It has to equal my time rate of change, so d time of this expression for U. So that's Ts minus T initial over 2 delta T A rho C. Okay, in this problem, what is constant? So Ts is not changing. We're holding that constant with time. T initial is not changing. So these are actually constants here. What's changing? Delta T is changing, right? My thermal depth is changing with time. So that can't be pulled out. But the areas can be pulled out. Rho C are constant. So if we simplify this a little bit, we end up with, let's see, this cancels out, this cancels out. So we get 2 times k over rho c equals delta t, time derivative of delta t. That's just algebra to rearrange that. Everybody see where that sort of came from? Just dividing constants out, right? Okay. So let's see. We have a derivative delta t dt. We have delta t, and then we have some constant stuff over here. By the way, this looks like a familiar constant group, k over rho c. That's thermal diffusivity. So this thing here, this is called alpha, thermal diffusivity. So you might see this. You can actually look this up in ease, right? You can just look that up. It's just a grouping of these three things together. What it tells you is how prone a given material is to spread heat. Right? So the higher the alpha, the more prone it is that, how do you say it? Like the more capable a material is of moving heat through its body. Yeah.
Were you making the assumption that the material properties don't enough temperature?
In this one, yeah. In this simple analysis, let's assume this is all constant. Okay, so we've gotten this far. Let's rewrite it this way then. We have, what just happened? We have 2 alpha equals delta t, d delta t dt. So what we're trying to do, I guess, is come up with an approximate way of saying, what's my, how long is it going to take to get to this point? Or another way of saying that is, what is this depth given some time? So I have this equation here, this differential equation. I just want to solve this equation. So let's do that. I'm going to solve that equation by what? By taking the integral of both sides. So this is a separable equation. On the left-hand side, I just have the integral. On the right-hand side, I have the integral. So what am I integrating with respect to? Sorry, let me do one thing here. Let me bring that time over. So we have 2 alpha d time is equal to delta t d delta t. So I'm integrating the left-hand side and I'm integrating the right-hand side. So the right-hand side is pretty clear, right? I'm integrating this with respect to d delta t. So I'm integrating the right-hand side with respect to the rate at which this thing is changing. This delta t is changing. On the left-hand side, I have to integrate that with respect to time, right? So you can do that. We can do that as a definite integral, but what we need to do to force it to line up is to do the integral from 0 to delta t on the right-hand side and 0 to t on the left-hand side. That just sort of forces them to line up. So at some time, that whatever the time is, that corresponds to whatever the delta t is. Okay. So doing this integral, we'd end up with 2 alpha time equals delta t squared over 2. And I can solve this then for delta t. That becomes delta t is equal to 2 square root of alpha times time. Okay, so this really approximate model now gives me the ability to say, give me thermal properties of this body, tell me what the time is, and I can tell you exactly how far this wave has moved. Right? So it's a simple analysis, but it's a pretty good approximation. So this time, this thermal wave depth is something you're going to want to put on your note card, right? You'll want to have this handy. It's just a really good back of the envelope way, just like other time constants that we've developed. It's a really good way to understand what's happening in the problem. We can also rewrite this a little bit. So I've run out of room, but I think if we just rewrite this in terms of geometry in the problem. So let's say, let's say what? So over here, let's call this position L. Let's see. Let me think about this a little bit. Sorry, make you erase. So let's say that we have some geometry. What I'm trying to do is figure out a way to solve this equation where time is on the left-hand side in terms of geometry in the problem. So let's say we have a plane wall again, and that plane wall has some fixed thickness L. I want to know how long is it going to take that thermal wave to move from 0 to L. That's what I'm after. So I'm going to substitute L for delta T. So we'll just say L is the length of the thing I care about. And then solve this for time. And we get something where it's equal to L squared over 4 times alpha. We're just solving the problem. But let's call this, instead of just time, let's give it a time constant name. And this is going to be called tau diff. Okay. So tau diff is just a different way of representing the same information, but it's saying how long is it going to take for the thermal wave to move to my position L. Again, it's another thing that you're going to use probably all the time in this type of analysis.